In this section, we talk about some of the predictors that are particularly useful in time series models and in forecasting. The first and relatively obvious one is to use a trend, a linear trend in your forecast. So you just simply set the predictor to be equal to the number of observations since the start of the series. So your xt is just equal to t, where t goes from 1, 2, 3, all the way up to the length of the series. One issue with using a trend is that you're making an assumption that that linear trend is not only valid for all of the data that you've seen historically, but that it's also valid for all of the future. And that's a pretty strong assumption. It might work for a short time period, but it's unlikely to work indefinitely. Another popular and useful predictor is when you have categorical variables, you can turn them into what are called dummy variables, which just encodes them using zeros and ones. So in the simplest case, you might have a variable which contains only two possible categories, say yes or no, or true or false. And you can code that as a dummy variable with ones and zeros. And then when you do the regression, you just simply regress against the dummy variable. And the coefficient associated with that dummy variable is the effect of yes relative to no. If you have a categorical variable which contains more than two levels, then you can similarly use dummy variables. You just have to have more than one of them. So here's an example which occurs in time series models. Suppose you have data that are recorded on weekdays only, and you want to put in the day of the week into your model. Then you can take the day variable, Monday, Tuesday, Wednesday, Thursday, Friday, repeating, and convert it into four dummy variables like this, where the dummy variable number 1 is coded as 1 if it's a Monday and a 0 every other day of the week. And then if it's a Monday again, it's coded as 1. So the D1 is a Monday variable. D2 tells you whether it's a Tuesday, it's a 1 on a Tuesday and 0 everywhere else. D3 is the Wednesday variable. D4 is the Thursday variable. And you don't need the Friday variable, because if all of the others are 0, then you know it's a Friday. So you can code a 5-level category into 4 dummy variables. And in general, you always need 1 fewer dummy variables than the number of categories. It's a very common beginner mistake to use a dummy variable for every category, which gives you 1 too many. The trouble is when you then go ahead and do the regression, there'll be numerical problems with it. There'll be rank deficiency in the matrix of predictors, which means that the regression becomes singular and inestimable. So the solution is you leave out one of the categories, and then the coefficients of the dummy variables for the other categories are relative to the omitted category. So in this example here, the coefficient for Monday is the value of Monday relative to Friday, which is the omitted one. And the coefficient for Tuesday is the effect of Tuesday relative to Friday, and so on. If you've only got one categorical variable, then another solution would be to omit the constant from the model. And then you can have the same number of dummy variables as there are categories. But if you have a constant in the model, or if you have more than one categorical variable to code, then you have to make sure you omit the dummy, one of the categories, so you have dummies only for the other categories. So in time series, it's very common to do this for seasonal data. So if you had quarterly data, you'd have 3 dummy variables. For monthly data, you'd have 11 dummies, and so on. And it doesn't matter which category you omit, as long as you're aware which one you've omitted, so that you can interpret the coefficients appropriately. For daily data, if you're observing on all 7 days of the week, then you need 6 dummies to code it. Weekly data is problematic because there are not an integer number of weeks in a year. So putting in, treating weeks as a 52 category variable is not actually correct, because you're going to get the days at the end that are not part of any of the first 52 weeks of the year. And so we need another solution. We'll come to that shortly. You can also use dummy variables for other problems. So suppose you have an outlier, you can put in a dummy variable where it's 1 on the time when the outlier occurs and 0 everywhere else. And that basically zaps the effect of that particular observation. You can put in dummy variables for public holidays. So you can have a 1 if it's a public holiday and 0 otherwise, and that gives you a public holiday effect in the model. So any time you can think of, when something is true or not true, you can put a dummy variable in to code it. So let's look at a simple example where we use some of these ideas. So this is the Australian quarterly beer production, which we've seen in previous chapters. And if you look at it, it's clearly seasonal, and you might think there could be a trend there. So let's try fitting a model with a trend and some seasonal dummy variables. So the regression model is simply yt is equal to a constant plus beta 1 times t, so that's the trend. And then you've got 3 dummies. We've left out quarter 1, so we've got a dummy variable for quarter 2, for quarter 3, and for quarter 4. So the interpretation of beta 2, beta 3, and beta 4 is the effect of that quarter relative to quarter 1. To fit this in Fable, we can simply use the TSLM function, which stands for time series linear model, and then our data set doesn't actually contain a trend variable or seasonal dummy variables, but we can create them on the fly using the trend function like that and the season function like that. And so that will automatically create a trend variable and include it in the regression, and the seasons function here will automatically create enough seasons for the type of data it is. So it'll look and see, okay, this is quarterly data, I need 3 seasonal variables. And you can see from the output, the trend variable has a coefficient of minus 0.34. So that's saying that it's the beer production is decreasing by 0.34 every quarter on average over the series. And you've got season at year 2, year 3, and year 4. So that means the quarter 2 seasonality. So season year means that it's repeating every year, and the 2 tells you which quarter it is. So quarter 2 tends to be minus 34, so 34 less than quarter 1. Quarter 3 is 17 or nearly 18 less than quarter 1, and quarter 4 is nearly 73 higher than quarter 1 in whatever units the data comes in. So it's nice and interpretable. Let's have a look at the fitted values for this particular example. So here we've just augmented the model, and that gives us access to the dot fitted variable, and then we've overlaid the beer data and the fitted values like so. And you can see it on the face of it, that doesn't look too bad. It looks like it's fitted the data reasonably well. Although you might observe that the last quarter, so the last part of the data set and the peaks have been overestimated at the end, and at the start, the peaks tend to be underestimated. So that's a suggestion that maybe the model's not quite right. Here are the fitted values against the actuals, and you can see the effect we were just talking about, where this is not lying along the line, which is if we looked at the time at which those observations occurred, you could see that it's overestimating at the end of the series and underestimating at the start of the series. And here's a plot of the residuals with the ACF and the histogram. Yeah, that looks okay. And here are the forecasts obtained from that model. Notice that when you're doing the forecasting, you don't have to tell it what the future values of the trend are or what the future values of the dummy seasonal variables are. It will create them on the fly because we created them using these special functions. So those special functions sort of allow it to know what's going to happen in the future. Other places we can use these types of things, you can have an intervention. That's where something external has changed the output for a particular period, and that might generate a spike. So we can handle that like we handle an outlier, just have a 1 when that occurs and 0 otherwise. Other types of interventions might create steps. So the spike looks like this, where it's a 1 at the time of the intervention, at this time here, and 0 everywhere else. A step looks like this. So that's where the series might change level at some point, and you can simply model that with a variable that takes a 0 before the intervention and a 1 afterwards. And then you can have a change of slope variable, which is where you might have a trend and you want the trend to change slope. So then you have a variable which is 0 before the change, and then it just grows linearly afterwards with values 1, 2, 3, a number of periods since the change in the slope occurred. We'll talk a little bit more about that later in the chapter. You can also deal with holiday variables. So if you have monthly data, then you don't need a holiday variable for Christmas because it's always in December, so it's always going to be part of however you're handling the monthly seasonality. But if you have a holiday that moves so that it's not always in the same month, then you can handle that with a dummy variable. So for example, Easter, which is sometimes in March and sometimes in April and sometimes partly in March and partly in April. So you can use a dummy variable, which might say if you think Easter is going from Good Friday to Easter Sunday, then if any part of that is in that month, you put a 1 or a 0, or you might do it proportionally. You might have a variable which is the proportion of Easter that falls in that month. Similar types of ways of modeling holidays can be applied for Ramadan and Chinese New Year, where they're moving through the Western calendar. Another type of variables that occur in time series regression are where you have distributed lags. So that's where you've got a variable that the effect of that variable might not be entirely in the period that in the current period. It might have an ongoing effect. And a classic example where that occurs is advertising. So we can have advertising last month can affect sales this month. And so when you build a model, you want to put in not only the amount of advertising dollars that you've spent this month, but how much you spent last month and 2 months ago and going back as long as you think the advertising is likely to have an effect. So that's called a distributed lag model, where you distribute the effect of the predictor over a number of lags. And then the last one I want to talk about is a special way of handling seasonality, which is particularly useful if you've got long periods or if you've got non-integer periods. So you can handle seasonality using pairs of sines and cosines, which are called Fourier terms, named after the French mathematician Fourier. And they are of this form. So you have a sine term, which is the sine of 2 times pi times k times t on m, where m is the length of the period. So if you've got hourly data, for example, m would be 24. So the number of times you observe something before it starts to repeat. K is an index, so k begins at 1 and then increases. And then you have a pair of these. You have the corresponding cosine term as well. And then in the regression, so here's a regression where you have a linear trend here, and then you've got these sines and cosine terms here. And you have a certain number of them. So you might have only 1 pair of them, or 2 pairs of them, or 3 pairs of them, and so on. And it turns out that any periodic function can be approximated by sums of sines and cosines of this type for a large enough k. So you just have to pick k big enough to handle the complexity of the pattern that you're seeing in the data, the complexity of the seasonality. And you can choose k by minimizing the AICC. We'll talk about how that works in a regression context in the next section. This is called harmonic regression because it's modeling harmonics. So each of these pairs of sines and cosines gives you another harmonic. So it's analogous to what happens with sound. In Fable, we can easily do this by using the Fourier function and the K tells us how many of these terms to include. So you just have to choose how many of them you want in the data set. And again, it's picking, it'll identify the appropriate M automatically by looking at the series, the Y series, and seeing what the time index is. But you can specify a particular period. You can override the default period by another argument inside Fourier, which gives you the how many periods it wants to go before it repeats. So let's look at how that works in a particular example. So here we have the beer production data, and I'm using Fourier K equals 2. So I've got 2 pairs of sines and cosine terms, which gives me 4 extra coefficients, but I've only got 4 quarters, so I can't fit 4 coefficients. I can only fit 3, but it automatically drops 1. So it's dropped. So you see here, this is cosine 1, so that's the first cosine term, the first sine term, then you've got the second cosine term, but you don't have the second sine term because it's not needed in this model, and in fact is equal to 0. You'll notice if you compare this with the results we had before, that the intercept, and let's go back to the results we had before, it's way back here somewhere. Yeah, so compare the intercept and the trend. So we've got 441.8 minus 0.3403, and then some different values for the dummy variables. If we go to the back to here, you'll see that the intercept is different, but the trend is the same. And all of these things are different, but all of the other bits down here, they're all identical because it's actually the same model. It's just been parameterized differently. But the forecast from this will be identical to the forecast you get if you use seasonal dummies. Let's look at another example. This one is the expenditure on cafes, restaurants, and takeaway food services in Australia every month between 2004 and 2018. And you can see that it's trended, that it's seasonal, and the seasonality is relatively complicated. Let's see how we go handling this with sines and cosine terms. So here's some code to do all of the possible models that we could have with increasing numbers of sines and cosine terms. So we start with just 1 pair of terms, and then 2 pairs of terms, and so on. The largest number we can have is 6 pairs of terms, because that gives us 12 coefficients, and there's only 12 periods in a year, 12 months in a year, and we need 11 coefficients to handle that. So the last pair of coefficients in the model with K equals 6 will actually contain only 11 of the resulting coefficients. Okay, let's see what it looks like. So here's K equals 1. So we just have a single sine and a single cosine term, and the estimated pattern is basically a sine function with a linear trend in it. Then if I increase to K equals 2, you can see that the seasonal pattern is slightly more complicated. And as we increase the number of terms in the model, that's K equals 3, the ability of the model to match the complexity of the pattern increases. There's K equals 4, K equals 5, which is now looking pretty close to what the last few periods have been. K equals 6, you can hardly see the difference. There's K equals 6, there's K equals 5. The additional parameter, when we increased from K equals 5 to K equals 6, has really not done anything. Okay, so Fourier terms are really useful for handling seasonal patterns, and we can approximate any periodic function by sums of sines and cosine terms. We just have to choose how many pairs of terms we want. So we have to choose the value of capital K in order to model the patterns that are in the data. We'll look at how to do that in the next section. But for now, just notice that K must be less than or equal to M on 2, where M is the period of seasonality, because that will give us, because there's 2 parameters for every K, that will give us M parameters, which is 1 more than we actually need. Interestingly, and really importantly, we can have non-integer M. So if we have weekly data, where M is around 52.18, a little more than 52 weeks in the year, then we can just put in the correct M, the average number of weeks in the year, in the denominator, and it will work fine. So it's a way to handle weekly data. With none of the other ways we've looked at will handle weekly data properly, because in the previous models we've looked at, we've always needed M to be an integer, whereas here we're allowing it to be a non-integer. And it's particularly useful if M is really large. So, for quarterly data, we would not normally need to use Fourier terms because M is only 4 and seasonal dummies work fine. For monthly data, we normally wouldn't use them either because M is 12 and seasonal dummies will handle, you can handle it with 11 coefficients, which is usually not too many. But once you get above 12, then these types of ways of handling seasonality become more important. So from hourly data, for example, where M is 24, I would normally use Fourier terms, not seasonal dummies, because I can use fewer coefficients with Fourier terms than if I use 23 seasonal dummies. As I said, for weekly data, you have no other way of doing it. So for large M and for non-integer M, this is a particularly good way to handle these types of models.